Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's a real pleasure for me to welcome everyone here in the Smithwick Auditorium and everyone watching or listening on the web to the 10th annual Silicon Valley Astronomy Lecture Series. Tonight, I'm delighted to announce that our speaker will talk about the Cassini Mission, a mission to Saturn, which is revealing wonderful things about the planet, its rings, and its family of satellites. Let me begin by saying that the program is co-sponsored by 4 organizations: the NASA Ames Research Center, one of the premier NASA centers around the country engaged in research and education; the Foothill College Astronomy Program, which offers day and evening classes for everyone, regardless of background, in astronomy and many, many other subjects; the Astronomical Society of the Pacific, a 120-year-old organization dedicated to what we do here in the lecture series, sharing the excitement of astronomy with a wider public; and the SETI Institute, the Search for Extraterrestrial Intelligence Institute, a scientific and educational organization devoted to the search for life in the universe. And I'm delighted to say that we have the executive director of the Institute here, and that's Tom Pearson. Tom, where are you? There's Tom Pearson. I now would like to introduce our speaker tonight. Dr. Mark Showalter is a principal investigator at the SETI Institute in Mountain View. His research focuses particularly on ring-moon systems, and you can't get a much better ring-moon system than the one around Saturn. Dr. Showalter received his BA from Oberlin, his PhD from Cornell, and he's been a member of the Cassini Mission science team for nearly a decade. So he had a key role in planning some of the wonderful observations that he's going to discuss with you tonight. He's also a frequent user of the Hubble Space Telescope, and he's involved with the observations of the rings of Jupiter on the New Horizons spacecraft, which is right now on its way to heroic little Pluto, which, although demoted, is not forgotten. Dr. Showalter has to his credit the discovery of Jupiter's outermost ring, Saturn's moon Pan, and 2 moons and 2 faint rings around the planet Uranus. So this is a man who really knows his way around the outer solar system, and he's going to regale us today with information about Saturn's restless rings, the latest results from the Cassini mission. It is a privilege for me to introduce Dr. Mark Showalter.
Do we sound okay? Thank you all for coming tonight. I'm really delighted to see such a crowd. I should also say, just as a matter of introduction, that the Cassini project, you're seeing one of the images of Saturn as Cassini approached Saturn back in 2004. This is your tax dollars at work. And so thank you not just for coming, but thank you for making this project possible. And one of my hopes for this evening is that over the next hour or so, I might be able to give you a little bit of return on your investment. So thank you. And I also just was reminded as Andy discussed the wonderful new telescope you have here at Foothill, how many people, actually can somebody turn the house lights a little down? Anyway. How many of you have actually ever looked at the planet Saturn through a telescope? Let's see a show of hands. Hey, that's pretty good. It's cheating if you used a camera. It's cheating if you used an imaging system. It's cheating if you use a spacecraft. Does that rule anybody out? So, okay. Well, I had the experience of looking at Saturn back in my high school days. Welcome, by the way, to all the high school students here. And I'm afraid to say it didn't look quite like what you're seeing now. I was in my backyard in suburban Philadelphia, and on a really, really good night, it might have looked kind of like that. Actually, it really wasn't a very good night very often in suburban Philadelphia. We always had a lot of atmospheric turbulence and so on, and that meant it kind of went in and out of focus and moved around a little bit, and that made it kind of frustrating. And then, of course, we had a lot of light pollution in the Philadelphia area, so it was kind of looking through a glow like that. And, of course, my mount on my telescope was not very sturdy. You could just breathe on it, and suddenly Saturn would do this little dance as it moved across the sky because of my wobbling telescope. And then the mount also didn't do a very good job of tracking moving objects in the sky, so eventually my view would look something like that. Did anybody else have that experience? Yeah, okay. Sure, it seemed a little light. Yeah, could we please, do I turn the lights down? No, just please turn the lights down a little bit, yes. Okay. Well, let's bring Saturn back. Okay, in its somewhat corrupted form here. If you saw that site, something like I did, and were inspired by it, found it compelling and fascinating, we're in good company. And it helps to appreciate now a little bit of what Galileo himself went through when he pointed the first astronomical telescope at Saturn in about 1610. And this was his drawing, his actual drawing before it was trademarked by the Walt Disney Corporation. And it shows a very puzzling sight. He had already seen the moons of Jupiter. He knew about little dots moving around big dots, as you see if you ever look at Jupiter through a telescope. But he had not seen anything like this. These were 3 circles, a big one in the middle, 2 on the side, and the 2 on the side didn't seem to move. Galileo, it's not clear if he ever actually figured out what he was seeing, but some of that work was carried on further by a man named Cassini Huygens. And in the year 1659, we're coming up on the 350th anniversary, he published the first book on Saturn. And at that time, he assembled all of the pictures that had ever been drawn of the system, and they make an interesting progression of our understanding of what this thing was that Galileo had seen. This is Huygens' rendering of Galileo's first drawing, and then we'll just kind of step through them. We're also seeing seasonal changes as the rings of Saturn open and close as appearing from Earth. But you can see that it's a very mysterious system. We're slowly maybe, there we kind of maybe got it right. But that's a little more fanciful, and that's completely wrong. And, but finally, Huygens himself in 1659 in Systema Saturnium published his drawing of the rings of Saturn. And he was the one to figure out, as you can see, well, okay, it's in Latin, but if it were in English, you could see it's actually not that hard to translate the Latin. And there highlighted, it says, Annulo singit, okay, I don't pronounce Latin either, but it says, the ring, annulo, is this working? I'll use this one, sorry. Okay, the ring in circles is thin, is flat or planar, is nowhere connected, and is inclined, inclinato, to the ecliptic. So that was the moment with this picture coming into view that brought ring systems into the human imagination for the first time. Well, that was a long time ago, and I'm going to jump ahead quite a distance now to what I would consider the modern age of ring science. We really didn't get a chance to understand rings till we started to be able to send out spacecraft. And here's an image from 1980. Voyager 1 was the first spacecraft that we sent out to Saturn that had a camera on it. And this is one of the images as it was approaching in fall of 1980. Very exciting. You can see all kinds of structure. You can see maybe some little striations in here. These are called spokes that we had no reason to expect. There is more structure in the system already than we had any expectation of. And that was when things began. And there was, I've done a lot of work with the Voyager images, and unfortunately for every image like that, there's also one that looks a little more like that, which is an interesting story behind it, which is that with any spacecraft, you always have a strict budget of how much data you can send down to Earth. And everybody knew the atmosphere of Saturn would be very interesting, storms and eddies and all those kinds of things that happen in atmospheres. Nobody had any envisioning that the rings would be anything more than kind of bland and uniform and pretty much the same yesterday, today, and tomorrow. So the spacecraft was actually programmed to take these images and then edit out the rings and send the rest back down. The imaging team corrected that error with Voyager 2, and we have an extraordinary data set, even regardless of this little problem. But for any budding young scientists or astronomers out there in the audience, you know, I take away the moral from this: never assume that what you haven't seen isn't interesting. I think that's a good rule to live by. But that brings us finally up to Cassini, where I started my talk a moment ago. And here's my title: Saturn's Restless Rings, Latest Results from the Cassini Mission. Now, restless, that seems like a kind of strange choice of words. And the reason I put it in there is because we're learning so much about the rings today that make them not the boring, static, uniform system that the Voyager imaging team once actually believed wasn't worth looking at, or at least not spending a lot of data bandwidth getting the data down to Earth. And so studying the rings today is a lot less like studying a geologically fixed structure and a lot more like studying the weather. So I would be not living up to my job if I didn't show you a little bit about the Cassini mission itself before we move on to the ring system. Here you can see it, and I just want to point out these are people. They're dressed up in white because they want to keep the spacecraft as clean as possible before launch. But Cassini is a very large structure. It's the size of a small bus, for example, and so that's what we currently have orbiting Saturn. This large piece is gone now. That's called the Huygens probe. It was named after Christian Huygens, who, in addition to studying the rings, also discovered the satellite Titan, and that is the entry probe that was dropped into Titan. Several of these big booms and antennas coming off to the side are for magnetic field and such measurements. This is the high-gain antenna that communicates with Earth. There's some rocket engines down on this end, and the cameras and all the other instruments are around the side here. When we study the system, the engineers down at Jet Propulsion Labs in Pasadena did an amazing job of coming up with a tour that samples all kinds of views of the system. Now, this is only this ends about a year ago, so we're already about a year into the extended mission of Cassini. But we got a number of views when the system was edge-on to us. By orbiting in the equatorial plane of Saturn, we get a very nice view of the satellites. We often get flybys of the satellites, but it's not really optimal for studying the rings, for example. They're just slender little lines seen on edge. We also sample some other geometries where the spacecraft would be flung out of the ring plane and look down almost on the pole, in this case, of the North Pole of Saturn, and you get a very different view. Makes the rings people happy, also makes the atmosphere's people happy because they get to see the North Pole or the South Pole. We also get to stretch out and see a little bit more of what's going on in the magnetic field. I will unfortunately have to breeze through just a few of the wonderful images coming down of the satellites and the planet itself. We have a camera on board. It's a very fine camera, and this is one of the images taken through 3 different colors and then pasted together to make the full color that you see here. Saturn has a very turbulent atmosphere, lots of storms. It has bands and all kinds of structure in there. I'm sure if you brought in an atmospheric scientist, he could wax rhapsodic about all of the interesting things going on here. I'm unfortunately going to have to just move on now. We have a number of other instruments on board. One is an imaging infrared spectrometer. It doesn't have the resolution of the camera, but it gets a lot more information in terms of things like particle sizes, as we're shown here. It also measures chemical compositions of things. Quite a remarkable instrument. And here is a slightly garish rendering that came out of the spectrometer team just the other day. They used red to highlight the deep-seated thermal energy, the heat that is coming out of the North Pole of Saturn, and they pasted on top of it in blue measurements they had of the aurora that are coming down onto the particles coming down onto the North Pole and producing that image. We have a thermometer on board in the form of a far-infrared spectrometer. It measures the temperatures of things. And here I have painted the temperature across the rings, and we see some areas that are warm and some areas that are blue, and there are all kinds of interesting reasons for that, and unfortunately I can't do that topic justice tonight either. Here's a lovely view of the very large satellite Titan. It's covered in a smoggy atmosphere as seen by the cameras, And that's about all that the cameras can do with it, unfortunately. But as I said, we have other instruments as well. And in the infrared wavelengths, we can actually see through the clouds down, and we can start to see land masses and clouds and all kinds of other things beneath. Well, I mentioned the probe, the Huygens probe, which was dropped, I should say, it fell onto Titan, and before its batteries gave out, it actually safely landed on the surface. So here we are. This is the furthest human outpost on the surface of any planetary body. It didn't last very long. It wasn't expected to, but the geologists are very excited about identifying what are the components of all these different rocks. Once again, I encourage you to pursue this further if you're interested. Not a topic that I can cover in my brief time with you tonight. As the entry probe to Titan parachuted toward the surface, it got some interesting images looking down, and this was one of the more interesting, showing channels as if, well, actually flowing toward the left, presumably, some kind of liquid. Now, it's far too cold for water, but some kind of liquid is actually flowing, or has flowed recently, across the surface of Titan. That's a remarkable result, not seen elsewhere in the solar system, except, of course, on Earth. And finally, our radar instrument bounces signals off the surface of Titan, and it detects very rough areas, which are shown in yellow here, and very smooth out areas, which are shown in blue, which might be cheating, but it does drive home the point that these very flat areas are probably lakes. We have liquid methane gathering in lakes and collecting on the surface of Titan. Quite remarkable result. Titan is a truly extraordinary world that warrants further study by NASA. It's probably one of the targets that a future mission will go and spend a little bit more time on Titan. We have a lot of other satellites. This one happens to be one called Tethys. This is actually true color, which is a little disappointing because I can't see any color in there either. But not everything in the solar system gets to be colorful, I'm afraid. But there's a very interesting geology associated with some of the features here. You can certainly see craters indicating that this is a very, very old surface. And of course, that's from a distance. Cassini does very close flybys on occasion. And here you can see up close and personal some of the craters on Tethys. This one is not true color. It's kind of been enhanced. So I'm sorry to say that if you saw it with your own eyes, it would probably be much more like black and white. But that color enhancement gives us the capability to see things that would otherwise, our instruments let us see things that our eyes can't necessarily see. There are much smaller bodies, including Janus here, just 100 or 200 kilometers across, orbiting much closer to the ring system. And you can see it's had a very battered history. It's a small enough body that it is not spherical. The reason that satellites are spherical, and planets are spherical for that matter, is that they have enough gravity that they collapse. They pull themselves together into the smallest shape they can make, and that happens to be a sphere or something close to a sphere. Small satellites can be just look like big boulders because their gravity is not that strong. And unfortunately, in the interest of time, I am not going to say too much more about all the other extraordinary discoveries coming from the Cassini mission. We've been living at the end of a fire hose of data for almost 5 years now, and so I just couldn't do the rest of the topic justice. I'll barely be able to do the ring science justice. But I did want to mention, in particular, saturn.jpl.nasa.gov, a URL pretty easy to remember. That is the main outreach page of the Cassini mission. JPL, by the way, being Jet Propulsion Labs, is where the Cassini mission is managed. And so if you want to see more, there is a tremendous amount of information there. I just have a great time paging through that website myself every few days if I can. Many people ask, well, what are we going to do with Cassini now? And that's a good question. It can't run forever. The spacecraft is very, very healthy at the moment. And in fact, it was only slated to be a mission that was 4 years long, ending this recent July. And so we are already into what's been considered the extended mission. We have 2 more years officially approved by NASA headquarters. And then at a certain point in time, we are going to have to dispose of this wonderful spacecraft. And the way to do that is going to go out with a bang. This is tentative plans, but we expect NASA headquarters to approve it. At a certain point in time, we're going to fling Cassini. This, by the way, is the orbit of Titan. we're going to use a little boost from Titan to fling it so that instead of being in an orbit that flies over and outside the ring system to one that goes into that little keyhole between the rings and the planet. And we'll be flying within a few thousand kilometers of the surface of Saturn. We'll be flying just thousands or tens of thousands of kilometers over and under the ring system. It will be an extraordinary period for gathering our final data, but then eventually that orbit will evolve inward and it will burn up in Saturn's atmosphere. And that's how the mission will end, and we don't know when that'll happen. We're hoping for another good 4 or 5 years or maybe more, but that's out of my hands and above my pay grade, I'm afraid. Okay, oh, I went backwards, sorry. Okay, so now for the rest of my talk, I'm going to focus on the ring system. And here you can see it. I decided we should start off with a little bit of a roadmap. Right here, you have 3 main rings of Saturn. This is approximating true color. It's very hard to actually reproduce true color, especially by the time it goes through one computer and then another computer, and then finally projected on this very nice display screen. But so let's say it's approximately true color. But we can see the outer part called the A ring, the middle part, which is very bright here, called the B ring, and the inner part called the C ring. There's a gap between A and B, which is called the Cassini division. And there's a smaller gap near the outer part of the A ring, which is called the Encke gap. And there's a whole lot more structure. If you're up close, you can maybe see how much structure there is in there. And I'll be talking about some of that as we go on. Let me show you a slightly different view of the rings. Damn, sorry. Let's try that. Okay, we have 2 sides to the ring system. And the rings look very different whether you're looking on the lit side above or on the dark side below. What we see, for example, is that the B ring changes from being very, very bright to very, very dark. That's because the B ring is so jam-packed with material that you can shine light on one side, but very little light gets through to the other side. On the other hand, we have a small amount of material in this Cassini division, and that material actually scatters light very, very effectively, so that when you go over to the dark side of the rings, the so-called dark side of the rings, certain other areas get brighter. For example, the Cassini division is now very bright. The C ring is now very bright. The A ring is about the same either way. So you'll be seeing different sides of the rings, and sometimes it's very disconcerting when you think you know what a feature looks like, and then you see it under completely different lighting conditions. But I just wanted to prepare you for that. If you know your alphabet, we don't really have to stop at C. The D ring is an inner, very faint ring that is closer to the planet, off to the left, not shown. The F ring is this slender strand out here, and to make the alphabet as complete as it's going to be, E and G are very distant and very faint rings, and there is no H ring yet. So that is the Saturn system. I wanted to remind you of some other ring systems that I happen to be very fond of myself. Jupiter has a very faint, very slender ring, shown here in a Galileo image, as you can see. Uranus has 9 dense but very narrow rings, as imaged here by Voyager 2. And here is the Neptune ring system, and you can see maybe some funny arcs, some little clumps of material orbiting within the rings of Neptune. None of these planets has a system anywhere near as extensive as the Saturn ring system, but they each have their own special quirks and charms that make them all quite worthy of study. I'll be saying a little bit more about each of them as we go through the evening's presentation. Now, I've been working in this field for a long time, and because of that, I tend to throw around a certain amount of jargon. And I apologize in advance if I do that, but let me introduce you one of the words that is almost sure to come out of my mouth. It's a great word. The word is ANSA, and it shows up in almost no dictionary of the English language. It does, however, show up in the Oxford English Dictionary, where essentially every word in the English language shows up. Every word currently or having ever been in the English language. And ANSA comes from the Latin meaning the handles of a cup, and is a name applied to the apparent ends of Saturn's rings seen projecting like 2 handles beyond the disk of the planet. A beautiful word that is only used to talk about planetary ring systems, rather strangely enough. So here we have Saturn, and we have 2 ANSI, or plural of ANSA. As in general, most planetary systems have 2. All right, I'm going to show you a little bit of the physics behind planetary rings as we go along. One of the things that's really wonderful about planetary ring science, I will confess, is that you don't really have to be very smart. Collisions and gravity are just about all you need to know. And there are a few leftover bullets down below, which I will fill in a few gaps. But very, very simple physics is all we need to understand most of what we see in the Saturn ring system. What that means, for example, is that we don't need to know general relativity, which is quite a relief. And we don't need to know quantum mechanics. And quantum chromodynamics is right out. No quarks, no gluons, none of that stuff. Let's just put that all aside. And let's just get back to some very basic physics, gravity and collisions. So what do we know about gravity? Well, here we have a tree. And in that tree are apples. And believe it or not, apples fall. Newton is widely credited with this discovery, but actually it's been known for quite a bit longer than that. All right, so that's how gravity works. Well, let me show you an equation, not because I'm really going to talk about equations tonight, but just to make them sort of symbolic. This is Newton's law of gravity. And if you've studied a little physics, then you've seen this before and you know exactly what it means. If you haven't, don't worry about it, but just notice that it doesn't have too many letters, and there's no Greek, and there's no integral signs or derivatives or anything like that. Gravity is a pretty basic and pretty easy to understand piece of our physics. And nevertheless, let's just now move out to a slightly different environment. Suppose that's a really tall apple tree sitting out around on the Earth. And now we let go of that last apple. Anybody know what's going to happen? Well, it's going to fall. Believe it or not, apples fall no matter how far out they are. That's not maybe a surprise, but maybe you were expecting something to go into orbit. And the only way you can do that is if you give it a little bit of a push. So if you give something a push while it's out, it's going to now continue falling toward the Earth forever. The trouble is, unlike the apple, it's falling toward the Earth, but it keeps missing. And therefore, it stays in orbit. And that's gravity. Okay, let's move on to collisions. Have we seen these before? Okay. It's a pretty simple system, sometimes called Newton's cradle, and you've probably played with one. And even though we think we understand collisions, even this little system can do some rather strange and delightful things, as you may have noticed if you've ever played with it yourself. Well, this particular little animation has been idealized. It uses something called elastic collisions, collisions which do not dissipate any energy, and that's bad news for you and for me, because this will now run forever. And we all want to go home tonight, so I'm going to interrupt that. And instead use a different example now with something called inelastic collisions. Inelastic collisions are, suppose we took those steel balls and replaced them with, oh, I don't know, cotton balls or something, and the whole thing kind of damps down. So inelastic collisions are what it's all about in the rings of Saturn. All right. We now know everything we need to know to understand an interesting property of the rings. How thick are they? And I'm going to show this movie first. This was taken by the Cassini imaging team, and it shows Cassini going northward from the lit or southern side of the rings to the north or unlit side. There goes Mimas, one of the satellites. If you look out here, maybe you can see some little dinky satellites going around. Maybe you can catch the F ring, this slender strand outside the main rings, and so on. Now, I think that's quite a beautiful movie just because it gives you a sense of what it's like to be there. But, well, I'll interrupt it now. Now I'm just going to focus in on the middle few frames. Let's look at that again. Now I've identified a few features, such as the F ring and the A ring. There goes Mimas, and stop. The rings almost completely vanish when you look at them edge on. They are very, very thin. And in fact, even now, the fact that you're seeing the rings is because we're not exactly, we didn't take a camera at the exact moment that we crossed the plane. If we had, the rings would be truly almost invisible here. And how thick are those rings in reality? 5 meters. Now, I'm about 2 meters tall, not quite that. Look up, everybody. That's the ceiling, and I'm guessing that's about, from the floor to the ceiling in this room, something like 5 meters. So the rings of Saturn would fit in this room, from top to bottom. Just something I looked up on the web today. The world record for pole vaulting is 6.14 meters. So humans have actually pole vaulted across the rings of Saturn, which I think is kind of cool. But that's not the whole story, because we have the other dimension, and now I'm just going to throw a few familiar objects at you for context. Here are the Earth and the Moon as in correct proportion in size relative to one another, except they're not really that close, which is good, I guess. Here is how they would look in proportion and actually separated, and people maybe don't realize often quite how far away the Moon is compared to the Earth, but there it is. And here now is the ring system of Saturn, which fits rather snugly between the Earth and the Moon. So imagine a ring system now that is as tall as this room and extends out to the Moon. That is the system we're talking about. Well, why and how can a system be so incredibly skinny and out of proportion? That's a 30 million to 1 proportion, as I showed you. Well, let's begin by putting one of our little test particles in orbit, and now we're going to just turn the whole system on its side and say, what does it look like when something is circulating around a planet, but we're looking at the orbit from the side? Well, no big surprises. It goes back and forth kind of like that. Now, what happens if we tilt one of those objects? And now it's on what we call an inclined orbit. And if we put those inclined object, and then I've left in an open circle the kind of shadow particle before we gave it an inclination, and the inclined particle just goes up and down relative to the ring plane, crosses the ring plane twice each orbit. Let's zoom in. Okay, so now we're going to ride along with this ring particle in the rings of Saturn and say, what does it look like? And there we are. We're riding along in the rings, and an inclined ring particle is going up and down, crossing the ring plane twice each orbit. Now, that would be fine if there were nothing in the way. But in fact, here we have the rings themselves. And now we start the same process up, but now this guy has a little bit of a problem. In order to cross the ring plane, it's going to hit something. Those things are going to be pushed out of the ring plane. They'll hit something else. And in a very short order, the whole thing flattens down. Now, in reality, we don't have all big particles like this. The ring system is made up of a small number of big particles and a lot of little particles, but that whole system is of the order of 5 meters in thickness. And so let us consider, suppose we created a big swarmy ring that was almost half as thick as Saturn here, and then just let it go. All these orbits crossing one another, and what happens? The whole thing flattens by collisions, and the time scale for that is of order 1 year. So I hope you can now appreciate how you can make a system as skinny as this built room and extending from here to the Moon in a very short order. So rings are thin, and collisions and gravity are all you need to know to understand why. Now I'm going to go into a very interesting system we only recently, well, a few years ago discovered through the Cassini data. This is the D ring. This is a look kind of edge on, and I'm going to focus in on this region. This is the interior part. All of A, B, and C, all the bright stuff, is way off here on the horizon in front and behind. And here we're looking very close to Saturn, which is just off the side of the screen. I'm going to sort of do some Photoshop magic, just zoom in and stretch and all that stuff. It makes me a little bit dizzy when I do some of these things. I apologize if that affects you that way. But now I've drawn a line across the ANSA, this red line, as you can see right here. And there's some very mysterious stuff going on here. If you had a flat circular ring, it would be symmetric across this line. It would come in. Here's one that's kind of symmetric, this bright one. It comes in and it goes out, and that's fine. But you look at some of the other things, and you've got like one here that splits in half. You've got some features in here that just don't line up with one another. Very puzzling. We've actually seen it once before in some Jupiter features. And the way to understand it is that we have ripples in this ring system. They're maybe not even uniform as shown here, but if the ring system goes up and down, then a bright feature on one side of the red line becomes a faint feature on the other side of the red line. So here we are seeing vertical corrugations in the ring plane. Here's a wonderful close-up that was obtained fairly early in the mission. And in November 2004, we saw this wonderful repeating structure. It has a periodicity or a wavelength of 34 kilometers in November of 2004 when we first saw it. Well, that's always interesting. You see a lot of periodic features in the rings, but still you always want to know what's going on. Well, we looked again. In June of 2005, no, it's really more like 32 kilometers, not 34. And then, now it's 31. This system is winding up, and it's winding up at a rate that we can observe. How can that possibly be? Well, here is our explanation. I'm going to start off with a flat ring, and then I'm going to tilt the whole ring. Now, I won't say why. This is not normally something one does with rings, I should note. But we have an entirely inclined ring here. And then I'm going to let it go. Now, individual particles go up and down through the ring system, but those planes also kind of wobble. Every plane of an orbit wobbles. And the inner orbits wobble faster than the outer orbits. So as time goes on, all these things that started off inclined together are going out of sync with one another until you get something like this. And here we have a ripply ring. And this appears to be what we're seeing now in the D ring of Saturn. And we're seeing it get more and more ripply as time goes by. So going back and showing you what we've got now, we've got 31, and then going back in time, 32, and then 34. You can play this backwards. We actually know how fast this system is winding up. It's winding up as fast as it's supposed to be winding up because we know the properties of Saturn's gravity. That's all consistent. So let's play this backwards, and we find out that something took the rings of Saturn from this to this in spring 1984. Something happened to the rings that lifted them off of the ring plane by about 1 kilometer. Now, that's a really strange thing. That was shortly after the Voyager 2 flyby, so in fact, we missed it. But as time goes on, and by the way, my colleague at Cornell, Matt Hedman, who has done a lot of this work, I spoke to him the other day and said, yep, it's still winding up. So I don't have new measurements since 2006, but Matt has made them, and it's just getting tighter and tighter. So here's an artist rendering. I use artists a little bit loosely here. This is drawn by a friend on a chalkboard. But the idea is there's not that much material in the D ring. So something comes along, big meteor or something like that, hits it, bang, you throw a lot of material out of the ring plane just by that one impact. That material comes back raining down half a period later, and eventually it all averages out, and because there's not that much material in the D ring, you have in effect tilted the entire ring system. And that's how we got the system we see today, and something happened in spring of 1984. Some of you are probably not even that old in the audience, are you? Yeah. Okay. All right, another very interesting phenomenon, one that's dear to my heart, called moonlet wakes. And this has an interesting history from a colleague of mine. His name is Jeff Cuzzy. He works at NASA Ames. I believe he's spoken here in the past, in fact. And back in those days, the Voyager era, this is a Voyager image, we actually used pieces of paper. I mean, I don't think anybody remembers that stuff, but we did. And he was sitting in the Albuquerque airport, and he took this piece of paper, and he held it on his side and sighted down it kind of like this. I can do this in Photoshop. It's much easier. But anybody notice what's funny about this edge here? It is ripply. It goes out, in, out about 6 or 7 times. It's also got a funny ringlet that I'll talk about a little later too. But there is a wavy edge to the inner edge of this gap. This is called the Yankee gap. This is near the outer. This is in the outer part of the A-ring. Here now is a close-up obtained by Cassini. Totally glorious view, in my opinion, showing. I hope you can see the wavy edge on the inner edge, a couple of ringlets, and maybe you can even see faintly a kind of spiral pattern that I'll also talk about. Well, we now know, in fact, I'm happy to say that I found the little satellite Pan. I found it in Voyager data, but now we're seeing it quite clearly. This is just another image to illustrate how incredibly thin the rings are. Pan is only maybe 10 kilometers thick, and there it is sticking up like a bug on top of a record, if you remember what records are. Okay, so what's going on here? Well, let's take our little orbit again. Now I'm going to make it into an eccentric orbit. An eccentric orbit is a circular orbit that's been shifted a little bit off-center. At least the first approximation, that's all it is. Eccentric or eccentricity, it's the same word you might use to describe your Aunt Millie. But in this case, it means being a little bit off-center. Maybe that's the same as what it means. And I should apologize to any Aunt Millies in the audience now. But let's go, let the system proceed with a shadow particle still on a circular orbit. And it just goes around. So now let's zoom in and take another look. Now we're going to ride along with the ring particle itself. And what does it look like from that standpoint? Well, we've got our reference point, the open circle, and the ring particle is executing what are called epicycles as it follows a path around this guiding center. So we see a lot of epicycles in ring science, so that's why I wanted to introduce that word. So now let's go back to the Encke gap, and we put our satellite Pan in the middle, and we let some edge particles wander on by. They pass Pan. Pan has a little gravity, gives them a shove, and then they go into epicyclic motion. And that epicyclic motion, as seen in the orbit of Pan, is this wavy edge. So we get a wavy edge that is in front of Pan on the inside and behind Pan on the outside, because our outer particles travel slower than Pan and inner particles travel faster than Pan. So it's not a big jump from that particular silly little drawing I just did to this wonderful image. Well, there's more to the story, as you noted, because we have this spiral pattern as well. And I can pull up, this is a drawing I did long ago, showing what I thought a wake ought to look like. I never quite envisioned that Cassini would do such a wonderful artist rendering of it for me. But the idea is particles come past, and now you can see what happens to particles not just at the edge, but further and further away from the edge. They have the same kind of epicyclic motion, but they start off in sync. They can't stay in sync. And so particles tend to start grouping together and then spreading apart, and then grouping together and spreading apart, and so on. And that is exactly what we're seeing right here. This is a wake of the satellite Pan. Well, that moves us directly into an interesting topic called shepherding. What happens, why is it that Pan, a satellite, is in the middle of a gap? I mean, Pan has gravity. It pulls things in, right? And if you pull things in, shouldn't you collect stuff around yourself? How do you clear a gap instead? Well, that has to do with the subtlety of the ring dynamics. Now, I'm going to show this little animation, and there's a little flash going on every time the particle goes through one of these dense regions. Let me show that again, just to make sure that's clear. So what happens is that flash is my way of representing that this is where collisions happen. So a particle starting off on the edge has a very special place every time it collides. It only collides when it's moving away from the gap, and it only collides with particles that are further out. And as a result of that, the entire gap spreads outward. And that, in a nutshell, is a process called shepherding. Gravity repels in this very peculiar rotating environment. So here we are, another view of Pan. You can maybe see the wavy edges behind it and then in front of it, and some ringlets. And maybe you can see the wakes here. They're sort of subtle. But I want to pull your attention up here to the next gap out, the only gap beyond Encke, which is the kilogap. And this was the place where the imaging team has discovered a little guy called daftness. Daftness orbits in the middle of the kilogap. It creates a wake on a wavy edge, just like we've seen before. It's a very different character, though. If you look closely, you see that it's not just this nice in and out, what we call a sinusoid. It's like ocean breakers. It's like these are waves that are breaking on the shore. The reason for that is very similar to the reason that we have breakers if you go to the beach. If you're in deep water and a wave is going by, the wave is just fine. It can keep going forever. But you get into trouble when that wave is almost as deep as the water, as the water that the wave is rippling on. And the fact that's called nonlinearity. And daftness is creating very, very nonlinear waves that look like these breakers. And so that kind of ties it all together. A good friend of mine, Mark Lewis, has done simulations of all these things. He's routinely doing million particle simulations now with his team of amazing computers. And so simulating many of the interesting things that we'll see tonight. So here we have, in summary, two gaps in the rings, the outermost two gaps, Pan in one and daftness in the other. Well, that raises a very interesting question. What about all those other gaps? There are quite a few in the Cassini division, none then in the B ring, but then quite a few in the C ring. And the imaging team has done extensive imaging of every one of these little gaps, and not a single satellite has been found in almost 5 years of looking. And some people have not given up hope. Maybe we just haven't looked deep enough. We haven't seen that 100-meter object that must be out there somewhere. But others of us are starting to wonder if maybe we just need to find another way to create gaps in the rings. So that remains a kind of open question and a mystery. Another example of shepherding, or quote-unquote shepherding at least, is here we have the F ring. This is an image taken by Voyager, so we're back to 1980 again now. and we see this little slender ring outside the main rings, and this was famously called the braided ring, because if you look closely, you see things going in and out and about and getting bright and clumps and bends and all kinds of weird stuff. So this led to, in 1980, one of my favorite scientific quotes of all time. The leader of the imaging team for Voyager, a man named Brad Smith, was on camera being interviewed for television at the moment that this image came down. And he saw it, and the interviewer saw it, and he asked Brad on camera, well, what is this telling us, Brad? And Brad was rather flummoxed by the sight, and what came out of his mouth, I will always remember it, is, well, there's a close-up, this is high on the list of things we didn't expect to see. I never had a chance to ask Brad what else was on that list. I regret that. He's retired now and doing just fine in Hawaii. But let's go back to Cassini now. Cassini is, the F ring is what we once thought of as the quintessential shepherded ring. It has a satellite on the outside and a satellite on the inside. They go by, this is Prometheus, this is Pandora, and the ring material is confined between them. And that kind of makes sense until you look a little closer and say Prometheus really isn't a very good shepherd because he's not keeping those sheep in nice, neat lines. He's in fact making a kind of a wake pattern there. And here's another image that just came out of one of the messes that Prometheus created in the F ring. And here are some more close-ups. I can almost never get tired of looking at the F ring myself. And well, the reason Prometheus is not a very good shepherd is that Prometheus is on an eccentric orbit, and in addition, the F ring is on an eccentric orbit, and in addition, Pandora is on an eccentric orbit. So here we have a little movie of Prometheus as it actually enters the inner part of the F ring, makes a little mess, as you can see. Then unfortunately, Saturn's shadow intervenes and we miss a little bit, but you can see this pattern repeating over and over. These are still called the shepherding moons, but they're just, they make more of a mess than a typical shepherd would. Well, we have some wolves in the pack too now, it appears, or in the herd, I should say. The imaging team has noted a number of little faint clumps that circulate around within or near the F ring. These are not satellites. These are little clumps of material. You can see they're kind of spread out. They're little clouds of dust. They must have some material in them because we're starting to understand what they do. Here's one example where we just run a sequence of F ring images. This is just mind-boggling to me too. But here we have a total eruption in the F ring that took place over about a 4-month period in 2006 and 2007. Well, one of my colleagues, Carl Murray, at Queen Mary College in London, and his colleagues has figured this out. And what he found is that if you take one of those dinky little wolf moons that I pointed out and put it on an eccentric orbit that is just flying over and over directly through the F ring itself, you can create a pattern in the F ring that is almost exactly like what we've just seen. And here, in fact, I'll put them two right next to each other. And so these wolf moons, as I've called them, that's not official, are actually disrupting the ring as we watch it. And then we should not maybe be so surprised when we see the effects of one of those impacts on the F ring, creating some mess like this. Or, for example, here in an edge-on view, you can see that there is actually quite a vertical distribution to the material that's been impacted in the F ring as well. By the way, just historical, interesting note, that's Pan right there. I think that's cool. So anyway, here's another very peculiar image of the F ring, and here's the numerical simulation carried out by my colleague Carl Murray. And if you stop it now for a moment, you can find a place in that integration where it doesn't do a bad job of simulating what we've just seen. So, that's the F ring is starting to make a little bit of sense, although it's kind of a big mess too. Propellers are a new phenomenon, only recently, well, only in the last few years discovered in Saturn's rings. Here we see some little, well, they're called propellers, I guess. They look kind of like propellers, and they're scattered across the A ring, just as very subtle features, kind of tilted. And here, from my colleague Mark Lewis, is simulation. And what that seems to be saying is that we are seeing individual particles, or the effects at least, of individual particles in the rings of Saturn. You put one, say, 100-kilometer object in the middle of the A ring, and it kind of distorts the ring around it. Particles try to stream by, get dispersed. Some of them even get trapped momentarily and stick to the particle. And you can create patterns that look in the Lewis simulations very similar to what we actually see in the rings. So we're actually almost getting down to the point of seeing ring particles. We haven't seen any actual particles themselves, but we're seeing evidence for them in all sorts of ways. Now, one of the ways is actually kind of surprising because you can see it from Earth. And that is, so what I did is I took this fairly generic Hubble image, by no means the best Hubble image of Saturn, going back to 1994, took it into Photoshop and gave it a little bit of an enhancement. And there it is. And what you can see if you look closely is the A-ring in particular is dark up here, brighter down here, then dark down here, and then bright up at this corner. This is what we call a quadrant asymmetry. And this has been known about for quite a while. We were never quite sure what to make of it, but now that we're starting to get down to the point where we can see the ring particles and even simulate them, this is a simulation that shows that the particles are not some uniform cloud of material the way we might have once envisioned. They form into groups. Those groups shear out. The whole thing is very dynamic, and it makes an almost spiderweb type pattern that comes and goes. But that spiderweb type pattern has a very characteristic slant to it. It's not radial. It's not longitudinal. It's in between. So here's a way to think about it. Here I've made a bunch of, I made a ring out of sort of canted structures, not radial, not in the longitude either. And I'm going to simplify that a little bit by just converting them to big fat bars. And now I'm going to let the whole thing flatten. So we're just changing our perspective on the system. And you see that in these zebra stripes, parts of the time on certain quadrants, right front and far left, we are looking at the slots between the zebra stripes. So we're seeing some dark space, and it gets a little darker. If we're looking across the zebra stripes, not much light gets through. So or more light gets reflected, I should say, and therefore it gets brighter. So this little piece of information that we've had for decades actually is caused by subtle aspects of what is going on in the ring system. Here is a, well, let me go back, sorry about that. Another feature where we have some little striations on the edge of the Encke gap now. This is the wake pattern of Pan, and now we're seeing some finer structure. And oh, this simulation makes me a little dizzy. I apologize in advance. But if you let Pan go by, as it just did, now we're riding along with the edge of the Encke gap as the wake pattern forms. Particles crunch together and then spread apart. And what you start to see if you look toward the edge and don't get too dizzy is that lines are forming. And I stopped that simulation in about now, I hope. Well, somewhere. Okay, it's coming to an end, I promise. There. Okay, so the particles have been crunched together and then pulled apart, and you've put them into little lines. So even though we're not seeing individual particles here, we are seeing the effects of the history of particles sticking together and being pulled apart. And there are a number of other places where we see what's called straw, patterns that are very distinct and unique in the rings. We see waves and other wave-like patterns as well. These are fairly, once again, easy to understand. All you need are collisions and gravity. And, but we're going to do a little horse race first. There's a special place in the rings of Saturn where a ring particle goes around 5 times every time the satellite Mimas goes around 3 times. So let's start counting and watch the race. Mimas always loses. I'll give it away. But here we go, 5-3. That location is right here in the rings. It's in the A ring. And it produces 2 ripply waves. One is called a density wave, where particles are, this propagates inward, and this means particles are getting close together, far apart, close together, and so on. It also has a vertical corrugation, a bending wave, which propagates outward and is very close by. So these 2 wave patterns are driven entirely by a resonance with Mimas. Now, you can look closely, you should see all kinds of wave patterns. The A ring is just totally filled with wave patterns, and every one of them has been identified as related to a satellite and a resonance disturbing the rings. Okay, back to kind of where we started. This is this view of Saturn ring system on approach, and I'm going to show you something completely different. Okay, maybe you saw that. It made the cover of National Geographic for one thing. What have we just done? Well, the key thing we have just done is gone around and looked back at Saturn from the dark side, from actually within the shadow of Saturn. and suddenly the system is glowing. Suddenly there are a couple of rings, G and E, that I alluded to earlier, but we couldn't see. Here they are in all their glory. The F ring is glowing tremendously bright. There's a weird little blue ring in here. There's just tremendous amount going on in here. And this was all entirely invisible up until now. This is why I need to bring in a few extra points about planetary rings. Everything else you need to know. So we need a couple of quick things, a quick lesson in light scattering physics, magnetism, and sunlight. And so let's look at light scattering physics. If you think about a ray of light, what happens when it hits a particle? Well, some of it refracts through. That makes a wonderful rainbow pattern that we see on rainy days when the sun comes out. You get diffraction around the particle, and you get reflection off the particle. These are simple enough. I'm using a little equation down here just to represent all of that. It's called Snell's law. It's the equation that gives the world rainbows. And if we now, say, send a stream of photons, particles of light, at a big particle, it scatters them back at us. This is called backscatter. Most of the light that has come from, in this case, perhaps the sun or whatever else source, hits a particle and bounces back. A big particle backscatters. And now big particles aren't really perfect spheres. They're kind of rough and bumpy, so maybe it's not as simple as they just showed you, but nevertheless, most of the light from a big particle scatters back. On the other hand, suppose a particle is small. And by small, I mean small compared to the wavelength of sunlight, part of what we see, which we're talking about very, very small particles. And then instead, the particle acts like a little magnifying glass and sends a lot of the light forward. This is now called forward scatter. And it is the difference between small particles and big particles. And is the difference between the image I showed you before and this. So these are now particles made, or rings of made of very, very small particles. And we call them dust. But reality is we're talking about millionths of a meter in size. That's actually the size of smoke particles. So although I'll refer to them as dust rings, these are really the smoke rings of Saturn, now that I'm talking about. And here's another wonderful example from Uranus. I showed you a picture of these 9 narrow rings, this image taken by Voyager. Well, Voyager had the chance to swing around to the far side, and there's what it saw. So the Uranus ring system is completely filled with dust, and we had no idea it was there until Voyager got around to the far side of it and looked back. There's before, and there's after. Magnetism. Have you ever played with a compass and a little magnet? And you know what the magnet does to the compass, twists it around. Well, what's going on here is that we can envision that magnet as producing something we call field lines. And those little electrons spinning around in that needle are trying to align themselves in a special way with that magnetic field. Well, it isn't just magnets that have magnetic fields, it's planets too. And here we're going to put a particle in the magnetic field of Saturn. Now, if that particle has no electric charge on it, it won't care. It doesn't respond to a magnetic field at all. But all it takes is one little photon to kick off one little electron, and suddenly that particle left behind has a positive charge. And then it starts responding. Now let's also tilt the magnetic field, because the truth is that it's tilted. And here's a little representative equation to describe the force of magnetism on a particle. The particle tends to go up and down, forced out of the ring plane, and follows these things we call banana orbits, where it just kind of bounces back and forth across the equator. So if you see rings that are not flat, it's probably because they're dusty, and that dust is being tossed around by the magnetic field. Wonderful example at Jupiter has as I showed you earlier, it has a very narrow ring, very dusty ring. This is, again, you can see the crescent of Jupiter over here. We're on the far side of Jupiter with the Galileo spacecraft looking back. And now if I pull up some enhancement, there is what we're really seeing in the system. And what's happening is dust, very fine material from the main ring of Jupiter, is being scattered off up and down and spreading out along the field lines of Jupiter. Pressure from sunlight. This is another rather amusing little process where a particle comes along, and I made a little armada of photons, particles of sunlight that hit it, and the first thing they do is just kind of push it off to the right, as maybe you can see here, so that this particle is now on an orbit that is shifted a little bit away from the sun as a result of that armada of photons. Well, that's not all that, and here's my little representative equation that says that photons have momentum, even though they have no mass. Well, let's watch the system a little bit more closely, and now I'm also going to tally up what we're doing to the energy of this poor particle. So it comes up here and poof, it just got hit in the face with a photon. And that took away some energy. So if you're keeping track, if you're keeping score down here, the energy went down. But you'll also notice it was a blue photon. You may have heard of the Doppler effect, where a train whistle is high-pitched when it's approaching you and low-pitched when it's moving away. Well, this particle was moving toward the sun. It was a high-pitched photon. And a high-pitched photon is blue and takes away energy, and that's what you can see here. Now let's go around to the other side. Another armada of photons comes along. Poof, but this one was red. So now we get back, we're hit from behind, so we're gaining back energy that we just lost up here, but we're only gaining back a red amount of energy because of the Doppler shift. And we let that process continue, and each time you go around, you hit blue, you lose a little energy, you gain back most but not all of that energy, and the end effect is that you are now on a smaller orbit. You have lost energy, and so what sunlight does over time is collapse orbits. They spiral inward to the planet. Here's a nice, very visual example of that. The outermost ring system, the so-called gossamer rings of Jupiter. These are seen edge on. It's kind of a funny, garishly colored image. I'm responsible for the color, sorry. But we have two fat tuna can rings. That's what we're seeing here. They're very thin. They're very transparent, I should say, but they are fat, and they go on into the planet, which is off to the left. And coincidentally or not, actually not, there is a satellite. I'll put it in Amalthea and Thebe at the outer edge of the red ring and another one at the outer edge of the yellow ring. And these are inclined, so they're going up and down by exactly the thickness of the rings that we see. And dust comes off of those moons and evolves inward under this drag force of sunlight's pressure, and that creates a beautiful explanation for those two rings that we see. Of course, that raises another question. What's that weird blue stuff out there? And that just drives home the point that we don't always know what we're talking about. In this case, probably the magnetic field, in addition to the pressure from sunlight, is tossing some of the material outward from Thebe, although it's very faint. Well, I told you my rings would be restless, and here's the most restless of all. This little blue ring, highly color enhanced, was discovered in the Cassini images. It showed up because of its blue color. It was kind of different from its surroundings. That ring was not there in the Voyager data. That ring is less than about 25 years old, and pretty remarkable. What it means is that somehow or other there was a particle there, a big enough particle to break apart. When you break something up into small enough grains of dust, you can make it visible, even though it wasn't visible originally. And this ring has come to exist in the last 25 years. Well, this ring gets a little bit more bizarre. It actually has a property, as shown here, where its outermost point, its point most distant from Saturn, tracks the sun. It is always pointed toward the sun. We have come up with a nickname for that. You may have heard it from botany class, heliotropic. Never before used to describe a ring. However, it is, for example, a sunflower, which always points toward the sun, is a heliotropic plant. Well, we now have a few heliotropic rings, and these rings, these little ringlets that I already showed you in the Encke gap, have been found to be heliotropic. And that's some kind of interplay between the magnetic field and the pressure of sunlight. Okay, I'm running toward the end here. I want to show you the G ring. This is a very peculiar structure, this is now a movie. The G ring, colleagues of mine have discovered, has a little clump in it. And that clump, as you can see, is going around. And we actually can explain that one with another little resonance. You get the idea. In this case, Mimas goes around 6 times every time the G ring goes around 7. And that creates a very, very special kind of interaction. And in addition to that, however, Mimas is slightly displaced. It is an eccentric object. And the two of those things together have the effect of letting particles basically be confined by little barricades that I've drawn as brick walls. And every time Mimas goes by, it gives a little shove to this particle and keeps it confined within that region, called libration now, where it's trapped. And that creates that little arc in the G ring. It also creates the arcs that we see in Neptune, where a little satellite called Galatea has a special resonant relationship with these 3 arcs. And finally, we're starting to see some new little objects. This is a the smallest moon we know about for Saturn. It's called Anthe. It's less than 2 kilometers across. And here it is with a dust ring coming off of it and spreading out around the planet. Turns out this is also in a resonance with Mimas, the 11 to 10 resonance. And here's another view, this time Anthe and another little guy called Methone, about 3 kilometers, and they each have rings associated with them that are incomplete, made up of dust confined by resonances. Getting outward now to the outermost ring, the E-ring, you can see it in the box, and in the box now there's also a little bright spot. That bright spot, let's take a closer look. That is the satellite Enceladus. Enceladus, we have known for quite a long time, is associated with this very, very broad ring. The E-ring is the broadest ring in the solar system. It encompasses several more orbits of satellites. It's utterly enormous. And we can see that it has a special relationship with Enceladus, but until some images came down a few years ago, we didn't quite realize what that was. Enceladus has plumes. It is sending out fine particles of dust and ice out into the Saturn system. You can see it's gray out here, not black, because we're looking through the E-ring. And so here we see the fountains of the E-ring at work. Well, Enceladus is a fascinating object. Any object that must have liquid water, as we now know, just within a few meters of its surface, and is sending out that ice and is sending out organic material as well, makes it a prime candidate for studies of maybe where life and how life comes to exist. You mix together liquid water and organics, and you get something kind of like the early Earth, and definitely worth studying some more. Here's a close-up distant view where you can see the terrain out of which these plumes are emerging, and they've even done some remarkable close-ups now showing the little cracks in the surface of Enceladus where these plumes come from. Okay, where do the rings come from? That's kind of the first question that I would have been asked if I didn't tackle it right now. I'm going to go through it very quickly because we don't know, but we have a few ideas. First thing to note is that the rings are very, very bright. And in fact, in this garishly colored image, blue represents water ice. This is made by the infrared spectrometer, and it's been encoded so that anything made of ice is going to be bright blue. The rings are made of water ice. Now, one of the things you know about water ice is that it gets dirty, especially if you've ever played in snow. Snow gets dirty. And the ring system of Saturn is constantly having these tiny black particles, meteorites, hitting it. So over time, we would expect that bright ice to turn darker and darker and darker and darker. And here it is now finally completely black, and it's gotten there in less than 100 million years. So if we expect the rings to be black after 100 million years, and they're not, that says to me the rings are pretty young, a lot less than 100 million years. Now, for comparison, our solar system is 4.6 billion years old. So the rings are very much younger than that. Here's answer number 2. Oops, sorry. Try it again. Might have to just advance. Okay. All right. Second reason why the rings are young. We talked about shepherding. There are satellites just outside the rings, and they interact with the A-ring, and because of that, they repel each other. The entire A-ring should collapse in something like 100 million years. So once again, 2 compelling lines of argument why the rings have to be quite young. Now, answer number 3. The rings can't possibly be that young. And the reason for that is that the question becomes, how do you make them? How did you make the rings 100 million years ago? Well, suppose you did the obvious thing. You had a satellite, it collapsed, it formed the ring. Probably wasn't quite that easy. But nevertheless, you create the rings, but the time scale over which that happens is not 100 million years, it's about 1 billion years. So the problem remains that we just can't make the rings fast enough to have them be as young as they are. Unless, and this is my solution to the question, we're just lucky. If we came along 100 million years from now, the rings would be gone. If we were here 100 million years ago, like the dinosaurs were, they would have missed them. We just got lucky. Here, by the way, is Mimas. This is an object about 400 kilometers across, has about the same total mass as the rings. So you needed to break apart a Mimas about 100 million years ago. So I can be forgiven now if I'm going to wrap up, and I'm also going to do a little bit of, if you let me indulge, a little bit of idle speculation. Why do we study rings? Well, maybe the slightly facetious answer, everything I need to know about the universe I learned from planetary ring systems. Here's one example of what we learn. This is a wonderful Hubble image of a distant galaxy, actually two galaxies in collision. What do we see here? We see spiral structures. Those spiral density waves are identical in dynamical origin to all those spiral density waves we see throughout the ring system of Saturn every day. Here we have two galaxies entirely colliding. I don't do galactic dynamics. I'm not going to say I understand what's going on here, but I bet you if you talk about how to understand this, the first things you're going to come up with are gravity and collisions, the same two things that define so much of ring science. Next example, Orion Nebula. This goes back to my backyard astronomy days. I had as much trouble looking at this as I did at Saturn, but one of my favorite objects was the Orion Nebula. It's right down in there. Giving it now, not my backyard astronomy treatment, but the Hubble treatment. It is a dense cloud of gas and dust out of which planets are forming. And if you look at some of these little stars, and if you look very closely in the Hubble data, you start to see over and over these disks, which are planetary systems in formation. Now, we can't get much closer than that, I'm afraid, except with our artists and our imaginations. Here's an artist rendering of what one planetary system might look like. It's got a couple of asteroid belts, some planets, it's got dust, it's got sunlight on that dust. Where have we seen all this before? It seems that planetary rings are the ideal dynamical laboratory where we can see systems that are otherwise completely and totally inaccessible, like planetary systems in formation. Let me make that a little bit concrete now. Familiar face. Can you all see the rabbit in the moon? It's my favorite. There's his ears, and there's his little tail, and his head, and so on. The many cultures of the world don't talk about the man in the moon. It's the rabbit in the moon instead. And it looks pretty compelling to me. Well, when the Apollo astronauts went there, picked up rocks and brought them back, found something very interesting. All those craters, all the ones you can see, are the same age, 3.8 billion years, plus or minus a little. Now, the moon is 4.6 billion years old. So what happened 0.8 billion years after the formation of the moon that cratered it so heavily? Well, the answer is something that at least theoretically we call the late heavy bombardment. And some dynamics colleagues of mine have come up with what I think is a pretty compelling explanation, which is that, now here's their simulation. We've got 4 big planets, Jupiter, Saturn, Uranus, Neptune, and a cloud of comets. And now we're back at roughly the origin of the solar system. We let this go, and the system evolves, and kablooey. And, oh, that's so much fun. Let's go back and show that again. So what happened to make this do that? Well, here's the before, and here's the after. The answer, according to the latest theory, is that Jupiter, this red circle, and Saturn, this white circle, went into a 2-to-1 resonance. Saturn ended up in an orbit that was exactly twice as long as Jupiter. That made a mess. And in Saturn, it makes density waves and other lovely things, but it doesn't have to do that. The after here is that Saturn has a big eccentricity. Uranus and Neptune have been tossed off into this big cloud of comets. They've been scattered helter-skelter, and some of them fell to the Earth. And this all seems to hold together as an explanation for the late heavy bombardment. It could plausibly actually have happened about 800 million years into the lifetime of the solar system. Well, the late heavy bombardment didn't just hit Earth, or hit the moon, it also hit Earth. And here's a wonderful artist rendering of the Hadean era of Earth, the hellish era, which is referred to as 4.6 to, oh, there's that number again, 3.8 billion years ago, a time when the surface was molten, it was very hot, not a pleasant place to be. And after that, according to the geologist, comes the Archean era. From arche, the same root as archaeology, it means beginning. And okay, maybe this artist rendering is just a little too tranquil, I don't know. But somewhere around 3.8 billion years ago, the environment of the Earth changed tremendously. So imagine that the dynamics of Saturn's system is telling us how this all came to be. So in summarize, remember that simple processes that I've summarized here, just a few of them, can create surprisingly subtle results. They can create things like this ripple in the D ring, these heliotropic rings in the Encke gap, as well as the wakes, density and bending waves in the A ring, this straw pattern in a density wave, this collisional event in the F ring, and this arc in the G ring. and these big fat tuna can rings at Jupiter. So all that happens with really simple physics. I always speculate that if you could start with just some simple rules of physics like this and create all that diversity, just imagine what would happen if you could have complicated rules, like, for example, this. These are some equations of organic chemistry. I tip my hat to anybody who understands this stuff. This is the reason I went into physics, not chemistry. But when I think about what you can do with 5 simple laws, and then I look at the organic chemistry, there are people out there who say, how could life possibly come to exist based on just the physical laws that we understand? And I look at that chalkboard filled with equations and say, how could they not? I think that's just, it's just based on what our universe does with its physical laws, life had to come to be. So there's my pitch for my role in the SETI Institute also. I left something out of this particular image when I showed it the first time. The artist was right and actually drew some little pads, some funny little features over here. Those are called stromatolites, and those are in fact the earliest form of life that has ever been found to exist on Earth. Colonies of microscopic organisms in shallow water. They appeared, all life, as far as we can tell, appeared on Earth about 3.5 to 3.8 billion years ago. So that late heavy bombardment started, which perhaps was triggered by a little resonance in the rings between Jupiter and Saturn, went on to trigger the chain of events that ultimately led to life on Earth. And isn't that kind of cool? So finally, I'm going to finish up. You've seen this picture before. I probably overused it, but to be fair, it is my favorite astronomical image of all time. In part, it's a triumph of politics. I was on the team that actually planned out the sequence of observations. We only had 14 hours inside the shadow of Saturn, and there was a lot to do. But nevertheless, I didn't mention something. I hope you can see it. People up close surely can. There's a little dot right there. That's not a dinky moon, and that's not a background star, and that's not a speck of dust. Maybe it is. It is actually the planet Earth. And here we are seeing the planet Earth from the far side of the rings of Saturn. Now, in the cameras of Cassini, that is nothing more than a single pixel, a dot. But for me, it's just very compelling. And it just reminds me that all of this ring science we do, and really all of astronomy, the ultimate goal and the ultimate destiny is a clearer and finer understanding of us. Thank you. Go ahead.
Yeah. The question I have is the composition of rings, even though it's mostly ice, there are other materials. Over time, does the composition of the rings remain, for the most part, amorphous, or does it tend to sort itself out?
If you look very closely at that very bright and color image, I could maybe pull it back, but maybe I won't try. There are very subtle color variations, and that seems to be related to somehow, every now and then, a bigger particle that's maybe slightly redder than everything else hits the rings. It eventually spreads out. But so you have very subtle color variations across the ring system. Nothing like as much detail as there is in the physical structure of the rings, the density of the particles. But there are compositional changes as you go across the rings. Interesting sidelight, though. One of the real goals of, actually, I've been working with the infrared imager on Cassini, and one of our expectations was that we would be picking out all the little chemical compositions of all these little different subtle color changes across the rings. And so far, we're almost 5 years into the mission. People on the team debate it, but I would say that we have not really convinced ourselves of any single chemical identification within the rings. So we call it dirt. That's not a very useful name, but that's the best we've got right now. It's surely made of carbon and silicates and things like that, but we don't know what that material is precisely yet.
Thank you.
Over here?
I have a question. In the early 80s, when I was studying this myself, after Voyager, there were there was a discovery of these spokes, I believe they called them.
Yes.
Seen at the ANSI, these radial structures.
Yes.
Do you see that now with Cassini, and is it still the electromagnetic levitation phenomena that it's attributed to?
Yeah, unfortunately, my section about spokes got left on the cutting room floor, as it were. Spokes are a very interesting phenomenon where there are dark features, and these were very, very prominent in the Voyager 1 and 2 data sets. Features going around in the B ring, mainly dark lines that would basically propagate as they went around. That's why they were called spokes. And they were seen a few times on the Hubble telescope as well. And the big puzzle has been that they have not been seen in the serious numbers on the Cassini data set that they were seen in 80 and 81. Now, our suspicion, and that's beginning to turn out to be true, is that it has to do with lighting geometry. The sun is actually sinking toward the ring plane as we speak at Saturn. We're going to have the equinox at Saturn coming up about a year from now. And as the sun gets lower on the rings plane and the sun sort of shines closer to the ring plane, spokes are starting to appear, and we're getting into a geometry that's much more similar to what Voyager saw. So it may well be that spokes are they've been there all along and they were masked. But as to an explanation, I know a few people who are studying that. I have not heard a definitive answer yet as to what's going on.
Thanks a lot.
Yes.
Yeah. What would the effect of all these collisions on a satellite going through the rings be? So what would the surface changes be? Could they be observed?
You mean a big satellite or a little satellite? I mean, the ring particles are probably up to the size of this building and no more. And those are just going through all the time, and they damp down by collisions. You're talking about a much bigger impact?
Like as Pan goes through the rings?
Okay, well, Pan has cleared out a gap for itself. So if something is big and lives in the ring, then shepherding says it will clear a gap. If it's not quite big enough, then it'll make one of those weird propeller patterns that we've seen quite a fair number of. But those are the only two choices. And then, of course, if there's an impact, if something comes in from outside the system, it could make quite a mess. That mess would perhaps change the ring system substantially, but it would all flatten out again, at least, very quickly.
My question is, what would the effect on the surface of the satellite be? On the surface, how would its surface change?
If the surface collided with the ring material. Well, actually, there's an example of that. I didn't bring a picture, unfortunately. The satellites, like Pan, that have not so much big ring material, but dust material in their orbit, all that material accretes onto the equator. And these are very funny shaped objects. They look sort of like very flattened hockey pucks, or maybe even flying saucers, some people have said, but they're very flattened, and then they have this big fat ridge on their equators, and that's because of small amounts of dust slowly accumulating on them.
Thank you.
On this side.
Didn't the Cassini actually pass through the Cassini gap on its approach to Jupiter?
No. That would have been a very bad idea if you saw the Cassini division has actually got material in it. That was discussed at one time, but it was deemed unsafe, and so it has passed through only the region between the G and the F rings.
Okay, the bigger
And it's considered even a kind of a hairy maneuver. They actually, if they were to pass it through a gap, it might be the Yankee gap, which is more empty, but it still has a couple of those little heliotropic rings in there that you want to stay away from. So that is why when they plan to end the Cassini mission, they will pass outside the F ring, get tossed a little bit by Titan, and then jump completely over the rings and pass through inside the D ring, because there's not really any place in the ring system that is considered safe.
Okay, another quick one.
Sure.
If there's ice particles, why do they not sublime and disappear?
what?
Why do the particles not sublime and disappear?
Actually, because they're too far from the sun. Sublimation, if you look at the Jupiter system, ice would basically dissipate very quickly. And so the Jovian system is made up of dark material. But at Saturn, you're safely further from the sun, and the time it takes for sublimation is very long.
Thank you.
Yeah. Thank you.
Actually, you kind of answered my question. It was about the safety of traveling through the rings, and maybe you could talk about the distribution relative to the different sizes of particles and what you know about that. You were saying that certain areas have smaller particles and certain
Right.
areas have larger particles.
Yeah,
What's
the dust.
How close are those particles together?
Well, the main rings have very little dust. There are big sort of basketballs and, you know, maybe golf balls is the range of sizes, and maybe a few as big as this room, for example. Something like the G-ring is very, very fine dust for the most part. We have actually, by accident, flown through the G-ring. Voyager 2 flew through the G-ring not knowing it was there at the time. And it did survive. There were instruments that picked up a lot of pings. Some of the magnetic field instruments got very disturbed by that. And actually there was a little bit of a clipping of the G-ring by Cassini because it turned out the G-ring was much thicker than we realized it was, and they sort of flew over the G-ring but a little bit too close. And there was very, very, I think one instrument sustained a little bit of damage, but nothing serious. So those dust particles are, you know, small enough that they won't do too much damage, but you really don't want to fly through them. Yes?
You mentioned these oscillations that happen within the ring, well, relative to the ring vertically. What is the time scale of these oscillations as these particles go up and down?
Oh, they go up and down
Yes.
once each orbit. So they start up, go down in half an orbit, and go back up in half an orbit. Those time scales are 8 to 14 hours, depending on where you are in the rings. So there are a lot of collisions. They happen very quickly.
Thank you.
Over here?
I'd just like to say, first of all, tax dollars well spent. I really appreciate this.
I agree. Thank you.
Secondly, just going back to the previous topic a few seconds ago, what's the relative velocity of these particles all humming around together?
Yeah, I should have. Many of the animations I showed you were, of course, highly sped up because that's what we need to see. Velocities within the ring system are thought to be of the order of centimeters per second at most. So, you know, that's about how fast they're moving. And so not very fast, but that's enough.
Okay. One last question. I'm just curious what your thoughts and opinions are of Larry Niven and the Ring World series.
Oh God, I read that years ago. Yeah, I think it's, I thought it was a great, I loved the idea. I mean, the math was all right. He does very good science side of science fiction writing, but it's not exactly the kind of system we're studying, I suppose. Thanks, yeah.
Another one on the density of the ring particles. If you had this visual image of like the ring being as thick as this room is tall, what could we envision like the density of particles like, let's say here's a basketball, where's the next basketball, how many golf balls would be in this room?
Yeah, in the case of the, well, I showed you some of the heat, and I showed you the fact that the B ring is lit on one side and dark on the other. What that means is in that 5-meter distance, very little sunlight gets through. Those particles are actually quite densely packed. I mean, you'd have to push your way through, literally. I mean, there'd be stuff coming at you slowly, centimeters per second is not going to be a problem, but you'd have to shove your way and burrow to get through the B ring. On the other hand, in the A ring, if you were to look down through the A ring, you would basically see about half the sky, and the other half of the sky would be blocked by ring particles. So lots of light gets through. It's fairly open. You still have to kind of push things out of your way. And then something like the G ring, you could probably be in it. That's this very faint dust ring. You could probably be sitting in the middle of the G ring and barely know it's there, except for those little pings of dust that occasionally hit your spacecraft or your spacesuit.
Thank you.
Yeah.
Out of curiosity, I've always been into the space program ever since, you know, the later, from 1975 with the Apollo missions all the way up to date. I was just wondering, how many light years is it from Earth to Saturn?
Oh, we're talking light minutes. It takes about 90 minutes, I believe is the number, for the information from the Cassini spacecraft to make it down to Earth, for example. So we're something like 7 or 8, Andy would know this, we're like 7 or 8 light minutes from the sun, and Saturn is about 12 times that distance. So it comes out to be something like 90 minutes.
Okay, thank you.
So now remember, the nearest star is something like 4 light years. So there's quite a big many orders of magnitude difference between the different distance of the nearest star, light years, and the light minutes that is the planets are from us.
Okay, thank you.
Sure. Okay, last question, I'm told.
You said that the particles are only moving a few centimeters a second. So that means that they're not really revolving around with the speed of the moons, for example.
I'm sorry.
You mean relative to each other?
It all depends on your frame of reference, and I made that unclear. A particle like Pan is going around Saturn every 10 or 12 hours. I think it's about 10. And so if you figure out 2 pi times 130,000 kilometers times, and you can figure that out. That's a big number. We're talking about many tens of kilometers per second. So that is the frame, that's the speed at which everything rotates. But now if you jump into the ring system and join the ring particles themselves and say, how fast are things kind of jostling around one another, that's where you get the centimeters per second.
Relative to each other. Then.
Relative to each other.
Thank you.
Yeah, thanks.
Well, let's thank Dr. Showalter again. Thank you for a dynamic and informative presentation. Thank you all for coming. We hope to see many of you back in January when we continue in the International Year of Astronomy. Good night and drive safely.